Swayam Prabha. Digital India. Educated India.
So in this session, I'm going to present an application of explainable AI. So thank you, Professor David, for the introduction. And thank you for PSC Asian at IIT Madras for providing me this platform to present my research virtually. Starting from day one, we have seen a lot of presentation based on machine learning and application of artificial intelligence and process engineering. But the application is not the application of artificial intelligence and chemical engineering is not new. It's like from like 3-4 decades, but it's not acknowledged as much because of some drawbacks, which I'm going to talk about right now, and providing a possible solution using an explainable AI with its application for diagnosis and multimode operation. With increasing digitalization and chemical engineering processes, the deep learning techniques has been like playing an important role in fault detection and diagnosis. However, these deep learning models are not human interpretable. Therefore, XAI is an emerging field which is providing solutions to understand and eliminate these deep learning models in order to make this deep learning system much better and interpretable. In this work, like an approach was to build interpretable AI system for multi-mode process monitoring. So before going much into our project, I will like to tell you about what is explainable AI. We have like data, and we have a black box machine learning model, which is termed as black box because we don't know what's mathematics is going behind in there to give the outcomes. So the user here is in ambiguous situation where it should trust the outcomes of the system, or why the system succeed, why this failed, or if rectify the error. So explainable AI provide the solution by providing decision and explanations to the user, which so that it can provide a feedback and understand why the machine learning AI model succeed, why it failed, can we trust on the model, and how the error, if there are any, can be rectified. XI techniques are divided into two parts. First is inherently interpretable models, and second is post-modeling explanation. For interpretable models, the common examples are logistic regressions and decision trees. These sort of models are explainable on their own because of their structure. And second class of models are required post-modeling explanations, which could be carried out using attribution and visualization methods. So in our research, we are going to focus on post hoc applications, which are further classified into different three different classes. First is visual explanation. Common examples are like class activation map, GradCam, in which we can get some contour plots and images in which we can understand that which factors are contributing towards the decision for the deep neural network. Second is local interpretable models, and the third is feature relevance explanations, which are about some attribution. It tells us which variables are contributing towards the decision. So let's get into more deep of our input attribution problem. Consider it's a classification model. We have a certain class of, we have various input in terms of variables, and the class is predicted using the classification model. So here we can, the attribution provide the information about which variables contributed towards the prediction of the specific class. So the overview of this attribution methods is on the basis of shapely value framework. It's a game theory approach. It's explaining by example for a more utilitarian meaning is like, for example, there is a project and there are three contributors, say X, Y, and Z, and they out of them the project they generated a profit. So the shapely value or the game theory approach will assist the us to decide how much each profit should be divided on the basis of contribution. So analogous to this approach, integrated attribution is proposed by Professor Dr. Sundarajan from Google in 2017. So this correlation game is analogous to input attribution problem, where we have profit function is the deep learning model. The individuals are input variables, and the profit share are the input attributions. So hence the Shapley value of input variable represents our attribution. However, the size of the problem is increases because of n input variable. The Shapley value requires 2 raised to power n combinations, and in machine learning, we have a leverage of including various class of and various number of variables. Therefore, there's a shortcoming, and for this, Dr. Sundarajan in 2017 proposed an integrated gradient-based methods, just under axiomatic attribution for deep neural networks. Utilizing this, we processed to our study, but let me more tell you about this. What integrated gradient means is here is the function, like we mathematically is the gradient of the deep neural function, which is evaluated over the input and the baseline, and integrated over the intensity of image. For example, here we can see that the baseline is alpha is equals to 0, which represents the baseline is the whole black image, and the alpha is equal to 1, the input image. So integrated it over the scale of from 0 to 1, we'll get the which variables or which pixels are contributing towards the decision of a deep neural network. So we developed this from the image data. We worked on how to work this out on the IG method is baseline. It's a key component, and it represents the complete absence of signal. That's which I showed in the previous slide. It was like black image shows the signal. And here the attributions are nearly 0, and an image classification is a black image. In fault detection and diagnosis, it is the average value of normal operating condition, which represent the absence of signal, which certainly implies that there are no faults in the process. So the XI technique assumes the limitation is the XI technique assumes single operating mode, which is not true in real world application. Process industries go to different modes and transition throughout its time period. Here we can see for the case study where we sampled like 1,000 time steps, and for say example, till 400 times samples, their mode, a significant mode was running over there, and the attributions was like nearly 0. After 400, there was a switch in the process, but they are like very deviated and noisy attributions. The reason behind this is that we are evaluating this explanation on the basis of single baseline, which is definitely giving us the noisy attribution. But if we are going to present these such outcomes to an operator, he or she will be confused. So therefore, we proposed an approach to compromise using 3 elements to explain a DNN decision for multimode operations. It comprises of state identification by real-time model selector, FTD module, and then exact explanations. So here is like we have the online data, we have the event expert. It's a supervisor system which have knowledge of transition state, normal state, and of different modes. Once the online data is sent to the event expert, it will identify the current operating mode of the system. If it's in transition state, then it's signals for system reconfiguration. If it's in a specific mode, then the data is sent to the FTD module. If there is a fault in the state or normal state, if the process is normal state, the data will be sent directly to the to create the bank of baselines, and both of these signals are sent to or XAI approach for sample analysis using a variable attribution method. Here, 3 steps are also involved. First is the attribution method, which I talked about. Second is attribution, which here the samples of time are like a sample over a window, and the variable selection using inseparability ratio. It will tell us which variables are more important, which will be driving the decision of deep neural network. So let us understand using a case study of a continuous still tank reactor. There is a single order exothermic reaction going over here, so A to B. The assumptions are there is a perfectly mixed temperature in reactor and jacket. The density, heat capacity, and overall heat transfer coefficient is constant, and the process is adiabatic. So we have like 3 faults were introduced in this study. First is reactor leakage, catalyst deactivation, and falling in jacket. And these are the number of simulated samples we use to train our deep learning feed-forward deep learning model. So in first one, we say that there is a leakage in reactor. Here we can see that for the scale variables, the till 400 samples, they are working in their normal operating region, but when the fault was introduced, they get deviated from their normal operating region, and this is correctly identified by our explainable AI model. The attributions are generated after 400 steps, and it shows that height is the factor which is driving the deep learning model to show that there is similar kind of results are evaluated using the activation in the catalyst. Here we can see that concentration is the most important factor which is contributing towards this decision. And in run 3, we see that for the falling in jacket, the temperature of reactor and the outlet concentrations are contributing towards this decision. Next, we worked on the case study of Tennessee Eastman process. It's a benchmark process with 52 variables and 20 pre-programmed faults. Out of them, we selected 5 faults for study. Here we can see, as in the similar case study, after when the time steps after 600 steps, there is a deviation in reactor cooling water inlet, and our attribution method correctly identified it, showing that due to this variable, there is the decision of deep neural network is based on this variable. Similar kind of result is obtained in loss in header pressure and the step change in inert composition of the B, which is acting as a feed in the process. Here we see that 4 variables are contributing towards decision, and the attribution methods is showing that X measure variable 34 is the most important, followed by X measure 10, XMV6, and X measure 8. So these kind of in all the case studies, it was showing a similar kind of results in both mode A and mode B. So in conclusion, the proposed approach we solved using multi-mode operations using 3 components, and the explanation is just in model development by understanding the basis of classification. The explanations received for each nodes are help to operating during real-time fault diagnosis. And in future, we are going to explore more techniques like anchor and retention methods to understand complex deep neural DNA decisions. Thank you.
Thank you. Any questions from Mike? Okay. I have a question. You talk about multi-mode operations, but
Yeah.
in your final result, you only show the Tennessee Eastman problem for a single mode. Have you done the mode? There are 2 modes, right? There are 2 different operation mode in Tennessee Eastman. I think there are 6 operation mode. So what is mode A and mode B? It seems that mode A and mode B are, so there are 6 operation mode in Tennessee Eastman problem. Which are
There are 6 operating modes for the G by H ratio on the basis of that. So the mode A talks about the 50-50 ratio, and the mode B talks about the product ratio of 10⁻90. So these are 2 models evaluated on a single deep learning
The
model.
same for 2 modes, right?
Yeah.
Okay, thank you.
Yeah, hi. So is your novelties in the mode detection, or is it in the fault diagnosis? Because you're saying you're attributing to some fault, which is the variable that is driving the fault. Or, I mean, I'm not able to understand what is the main contribution here. Is it the mode detection, or is it attributing which variable?
Yeah. The main contribution in this is understanding the decisions of a deep learning model. We can develop a deep learning model on the basis of that, and we can also evaluate pre-developed deep learning models. We don't know that how many modes it's working in, but we can. The main contribution is understanding the deep learning models. Training a deep learning model is like you have a set of data for different faults, and we can predict an outcome. But we don't know on what basis our deep learning model took that decisions. Sometimes, for example, there is a leakage in reactor, but it's showing that there is a leakage in reactor, but the basis could be wrong. It could be considering that there is a temperature surge, and therefore there's showing a wrong decision. So the main contributions lies under deciphering the decision of deep learning models.
Sure. Yeah. I mean, just a comment. Don't need to answer. You should
In the
compare
interest
with
of
the
getting
traditional
up,
methods.
Can we?
Yeah, we can take it offline.
Put off the discussion to. Okay. Thank you for the presentations. Okay. So we will have
Thank you.